They are ripples in space-time itself. The question of what happened before the Big Bang is intertwined with the multiverse. But space itself is not just a passive emptiness. It's actually got presence. They'll certainly change our perception of who we are and our beginnings.
Big questions, no easy answers. Dive into the mysteries of the universe with Unknowns. From the secrets of the Big Bang to the future of humanity. Discover what we still don't know. Tune in and explore the unknown. Do we know how the universe began? Sort of. In this episode, we'll explore what we know about the origins of the universe and the many questions that remain. Hi, I'm Kim Lochner and I'll be your Unknowns guide. Our host is David Christian, a historian, the founder of Big History, and the host of the Unknowns podcast. And our guest today is Ursula DeMarco, a professor at the Astrophysics and Space Technology Research Centre at Macquarie University in Sydney. Ursula's research focuses on stellar collisions, and we'll be talking about the origins of the universe. Let's start by asking what we do know about the Big Bang, the scientific theory for how our universe began.
Let me begin with my non-astronomer's version of Big Bang cosmology, and you can sort of expand on it. As I understand it, about 13.8 billion years ago, there was a tiny blob of energy that appeared, smaller than an atom, and that blob contained all the energy that is in today's universe. And it sort of exploded, and the explosion has been continuing ever since for 13.8 billion years. And as it exploded, that energy has sort of congealed into more and more complex forms. And of course, it leaves lots of questions open, like, where did that blob of energy come from?
I'd say that's an excellent explanation of the ropes of what we have and what we call the Big Bang. And the questions you just asked are also definitely the first question you would ask, wouldn't it? Where does it come from and why? Well, why maybe is going into a different realm, but definitely where does it come from?
What would you say we know with some confidence about the Big Bang?
We know with definite confidence that what we see today is a space. We see things around us, galaxies, well, stars first of all, but then we also know that we seem to live in an island of stars called the galaxy, and we know that there's lots of those galaxies around. And if you look at them one by one, they're moving away from us. And the farther the galaxy is, the faster it's moving away from us. So what is that telling us? It's telling us that in the past, they were closer. If now they're moving away and they're further and further and further, right? And so that if you wind back your logic, you find that you must have all been in a point at some point in the past. So that is actually quite simple, given that cosmology and Big Bang, et cetera, are complicated. And we'll see soon how complicated it gets. That idea, at least, is very simple. It puts us in a very firm grounding that the Big Bang happened.
So if I'm thinking of the universe as like a bubble that's expanding, have I got the right image in my mind?
So let's say yes and no. So yes, because it's an easy way to think of it. You know, we live in three-dimensional space. We have things all over, above, below, left, right. And so we think in those terms. However, the very fact that when we look at galaxies around us, they're all going away from us would make us believe that we are in the middle. But how on earth would we be in the middle? Why are we special? We're actually not in the middle. So the better way to think of the expansion of the universe, and indeed the universe itself, is to believe for a second that we are two-dimensional creatures. So think of us on Earth. Earth as a surface, it's round. We know that Earth is a three-dimensional sphere, but if you don't know that, if you don't have satellites that look at Earth, you might not know that. Earth looks pretty flat to me, so we're kind of thinking it's a surface, right?
And that's what many people thought for a long time.
That's right. Yeah. And in fact, many people still do. But let's not go there. Now, let's think that the universe is the surface of a balloon. Not the balloon itself, but just the surface of the balloon. And let's put a little dot on that balloon. That's us, Earth, or our galaxy or solar system, whatever you want to call it. And then we draw lots of other dots, and those are distant galaxies. And now we inflate the balloon. And as we do, it gets bigger and bigger. But of course, if you draw a line between any two dots, you see that the line is getting longer and longer. So if you were the dot Earth and you measure the line to all the nearby galaxies and the far away galaxies, that distance was going to get bigger and bigger. And if you were sitting on that dot, you'd see those galaxies moving away. So you'd think you're in the middle, but you're not. Now, if you are now a three-dimensional being looking at the two-dimensional surface of the balloon, you say, no, it's not in the middle. It's just logic that tells you that one point will see things moving away from it as if it were in the middle. And so we have this analogy now that this universe is like the surface of a balloon. And indeed, there are additional dimensions that we don't perceive as human beings, but that do exist.
So you just started talking about multiple dimensions. And now, we're all sort of familiar with the idea of multiple dimensions, and there's lots of science fiction about it. But to be honest, I do not understand what it means. Can you help us a bit?
I think we're not designed to understand multiple dimensions. We live in a three-dimensional world, and that's that. And I think the best way to understand multiple dimensions is to take one dimension down. So if you were an ant living on a very large balloon with no idea that the balloon had an actual middle, you'd find it very weird if somebody told you, hey, look, there's not just two dimensions, which is the surface of your balloon. You go left, you go right, that's it. There's actually a down and an up. And the ant would go, go on. But in fact, we know that we, three-dimensional beings, figure out and we can tell exactly that there are three dimensions, and the ant is just a little bit limited. So maybe there are beings out there that live in multiple dimensions, maybe 8 or 20, and go, those people that think there's only 3, they're just deluded.
So why do we need multiple dimensions to explain the story? I mean, the story makes plenty of sense to me as a bubble kind of expanding. Why do we need multiple dimensions?
Because the moment you have to actually explain what we have not yet talked about, which is the middle, the bit at the beginning, suddenly you just do not have enough freedom to express all the things that you need to account for, to basically explain how that beginning was, that gives us the complexity we see today.
Okay, so now can I go there? Because I remember when I taught big history, all my students wanted to know what was there before the Big Bang. So where did that little blob come from?
So you said before that something happened, a moment in, I dare not say time, because time may not have had a very good meaning before the Big Bang. But definitely the universe started at some point 13.8 billion years ago, not 18 billion years ago. So a moment happened and this Big Bang started. I used to think that time was created or formed or happened with the Big Bang, so there's no point talking about before because there was no time. However, I believe today scientists don't think this is a satisfactory answer. And the question of what happened before the Big Bang is intertwined with the multiverse. The idea that this little glitch that we call our universe is just one of many, and that may have preceded one or happen at the same time as another, like little bubbles that come into being and then take their own existence. And perhaps this model of the multiverse has an ability to explain quantitatively, which is what we want in science, about the many characteristics of our universe, how fast it's expanding, how accelerated that expansion is, and many other of the numbers that we can actually measure.
I seem to remember reading somewhere about something that was called evolutionary cosmology. And I think the idea was that if you have multiple universes, then it may be a bit like having multiple life forms. Some of them survive, some of them die very quickly.
Yes.
And it's the fittest that survive, that some have particular qualities that enable them to survive. Does that make sense?
It does make sense, except it's not clear what fittest might mean in that context. In our context, it's very clear that if there's oxygen, the creature that can make the most of that oxygen does very well, whereas those that are a bit not so good at making the most of oxygen, then they wither away. But there are real clear rules for our evolution in terms of biology. For the universes back then, who knows what it means? But it is true that some would have had a shorter life and some would have had a longer life. It's also true that our universe has specific characteristics. For example, the constants of physics, the gravitational constant that tells us how strong gravity is, for example, have a specific value, right? If G, the gravitational constant, was bigger, gravity would be stronger. And gravity may have overwhelmed the initial growth of the universe and led us to a big crunch very quickly. There is your universe that doesn't survive.
Am I right in thinking that very tiny adjustments to those constants would make a huge difference?
They would. And so the question is, would there be a universe without life, without enough time for life to develop the way it has in ours? And the answer almost certainly is yes. So those universes would have been maybe short-lived and maybe sterile in the sense of not having gotten any life in them. Now, life is another problem. And talking of complexity, that is very complicated. But
as a historian, I was always saying to my students, where's the evidence? So where's the evidence for the idea of a multiverse? If everything began with the Big Bang, how can we have any clues at all about what happened before it?
The biggest clue about the fact that likely there are other universes is kind of a little bit of an Occam's razor. We know our universe is expanding. We also know our universe is accelerating. Acceleration needs to be pushed or promoted by a force that pushes out, expanding the universe. Now, the only force we know of in this scales is gravity. And gravity does the opposite. It would bring the universe in. It would make it crunch, not expand and accelerate. So the question is, where is that force coming from? We call it dark energy, call it dark force if you like, because we have no clue what it's for.
And it was discovered quite recently.
Very recently. We're talking 25 years or so. The acceleration of the universe is pretty recent, certainly in my lifetime. In fact, when I was a student myself, we didn't know about it. It's during my PhD that this came about. Okay, so there's something that's bestowed on the universe, this force that is allowing it to accelerate. So the universe came into being, and there's something leaking in from somewhere else that is giving it this force. Somewhere else where? The universe is everything. So how can it possibly be somewhere else? This is maniac who would say somewhere else. So suddenly you realize maybe there's something that proceeds, something that bestows this energy onto little bubbles that we call our universe. So it's kind of tends to reason that there might be others before or after or at the same time. So we don't know fundamentally that there are other universes. We don't know that we have one of many that followed another one that maybe died too quickly. But we certainly, it makes logical sense. And I do know that real cosmologists, I am just a stellar physicist, do think about how can we find evidence of a universe, maybe a parallel universe, being there when there is no way of poking through ours and see if there's another one on the other side of the wall. That's not the way it works. I know earlier you talked about thinking of quantum gravity, and I'm sure we'll talk about it in a moment, and the idea that there might be a signal in this universe of the presence of another universe using the rules of quantum mechanics.
You've introduced the idea of quantum physics, and my understanding is that quantum physics is really about very small things. Now, the early universe we know was tiny, tiny, tiny. So quantum physics must have been involved. Can you give us a hint about why the idea of quantum physics is so important when thinking about the early universe?
Quantum physics is a set of rules, like most physics, that describes the very small. So when we talk about atoms, particles like electrons, protons, or even subparticles such as quarks, suddenly that's the physics you use. It is what gives you the rules of the game, how they interact with one another, how they travel, how they transform into one another. Quantum physics is so absurd when you think about it that people will ask, how do you know? Well, we know because using those rules, we make wonderful predictions that make your cell phones work, that make basically the world go around. However, the problem is that when we describe big things like galaxies, and we really need gravity in there, we tend actually not to need quantum physics. You basically really, you could put it in if you want, but it's just not an effect you would need. The problem is that either you describe the big with the theory of gravity, which is called general relativity, or you describe the small with quantum mechanics. Well, mechanics is just another technical word, means quantum physics. So is the world described either by one or the other? And what about somewhere in the middle that is not that small, but is got gravity and is also small enough that you need quantum physics? Do they clash? They do. These two physical theories are not mergeable. They're not interminglable. They do not work nice together. And scientists have tried for a very long time to see how the description of the world, which means small or large, could be with a unified theory that included gravity, of course, and also the rules of quantum physics. But nobody's really quite succeeded yet. Now, when we go to the Big Bang, there's a big problem. It's small, yes, quantum physics. It's also got the whole of the universe mass in it. So definitely, yes, gravity. So people have to make them work together. And there are lots and lots of flavors of theories that combine the two. Loop quantum gravity is one family of theories. Itself is I don't know how many there are in it, but there's several slightly different variations.
So this is an attempt to merge relativity and quantum physics.
Yes, to find a description that works for the Big Bang. And indeed, you actually need it there. So you're kind of a little stuck without it. In most physics today, most astrophysics, you don't really care because I really do not have to do quantum physics at all. I learned quantum physics when I was an undergraduate student, and then I promptly forgot it. And I'm really happy for it. But if I were to be a true cosmologist and really work on those problems, I definitely would need quantum physics as well as my theory of general relativity, which describes gravity.
And quantum physics, if I've got this right, might be easier to reconcile with the idea of the multiverse, because quantum physics allows the idea that the exact position of something can never be determined completely. So you always, in quantum physics, as I understand it, you always have it's as if you always have multiple identities.
Yes, everything is statistics. So you have a high chance of being right there where I see you, but there's a tiny, 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 tiny chance that you're sitting right where I am. And the fact that you have a large mass makes the chance of you being where you are actually so extraordinarily larger than the chance of you being anywhere else that you're actually where you are. But in little particles, which have little mass, they actually have a finite probability, means there's actually a little bit of a chance that they're not in the one place. They actually have a little distribution of positions, a little cloud of points where they could be. And this is the rule that makes quantum physics go round. And yes, so there's a chance for everything, even things that make no sense. There's a chance that right now, this glass right here next to me is going to go and sit next to your glass. It's just such a small chance that it's not going to happen.
Yeah.
But there is.
Are there lines of research at the moment? You've already actually sort of half touched on this, lines of research or of theory that you think might resolve some of these problems in the near future?
Yes. Theorists who work on loop quantum gravity, on string theory and other. These theories always have great names. I don't know, they must have a PR person working for them because it's just beautiful, like string theory. How cool is that? But these theories have been in the works for a while. So when you say soon, I don't know how soon that is.
Well, I'm talking about within the lifetime of students doing big history.
I'd say yes. Certainly advancements which will be tangible, like things that they'll be out in the New York Times front page saying somebody made a major breakthrough. And whether they'll change our life or not, they'll certainly change our perception of who we are and our beginnings, which matters a lot, I think.
And are there new observational techniques? I mean, I'm thinking of something like the James Webb telescope, or the fact that we can now detect gravitational waves. Will either of these new observational tools help us make progress with these mysteries?
Yes. fundamentally, we make big leaps with enabling technologies. So you mentioned the James Webb Space Telescope and LIGO, which is the gravitational wave detector that made the amazing discovery. So let's go through each of them. They're both very important. So James Webb is a large telescope, and it's in space. Space is great because air and atmosphere and clouds and turbulence is terrible for observation. So you want space. You also want to be observing in the infrared. The infrared is a wavelength or an energy of radiation that we can't see with our own eyes. It's less energetic, but it is what we can feel with our own hands when we're near a fire. That fire emits a lot of infrared energy. So the reason why it's important to look in the infrared is that, remember before I said that galaxies move away from us, and the farther they are, the faster they move. When something moves fast past you, it's the energy that is shining towards you changes wavelength, which means it changes energy. Now, when a galaxy moves away from you very fast, all the light that it's sending your way is in the infrared. So you need to be able to observe in the infrared to catch any of that light. Now, the farther the galaxy is, the more distant both in space and in time it is, which means it's close to the beginning of the universe.
So the James Webb telescope can look closer to the Big Bang than an ordinary light telescope or a radio telescope.
And in order to do so, you need a big telescope in space observing in this low energy light called infrared light, because the galaxy is moving so fast and so far away from you. All the light we see is in that wavelength, in that energy. So James Webb is perfectly equipped to look at the dawn. We could call it the dawn of time to be poetic, but ultimately it is only looking at galaxies, which means galaxies had already formed, which is not really close to the Big Bang. But it's very early on. So the James Webb is continuing. It is already making amazing discoveries of how things started. Now, gravitational waves are even better. Gravitational waves are waves. They're ripples, like the best analogy is a ripple on the surface of a pond. But instead of being ripples on a medium like water or air, they are ripples in space-time itself.
In space-time?
Yes.
And that's a fundamental concept in relativity, isn't it?
Yes. So we tend to think that we are things in space. We're a star in space. A person in a room is a person in space. But space itself is not just a passive emptiness or nothingness. It's actually got presence. And that presence, think of it as full of air. It's not quite it, but imagine there's something in space and you can send a wave through it, just like you can send a sound wave between me and you because there is air filling the space between us. It's not quite like that because air is something in space, but space itself is a thing. And that thing can be pinched, and that pinch will propagate out, just like sound propagates out from my mouth to your ear. Now, what can pinch space-time? If I do, it does actually a little bit, but insignificantly so. But a big stellar explosion, particularly one that is not spherical, but is maybe two stars coming together, orbiting faster and faster, and then colliding and merging into one, that will definitely pinch space-time and send out a ripple in all dimensions, it's 3 dimensions. And if that ripple gets through you, Earth, you can detect it. Not all of them, some are too weak, but we have now got the technology to detect the strongest ones.
These ripples can come from very, very early in the history of the universe.
Yes, they can come from a nearby neutron star merging with another neutron star, or they can come from that very, very early time. And they're not light, they're not electromagnetic radiation, they're completely a different thing. And because of that, they can come from earlier in time compared to this particular time from which all light, all radiation emerges, which is about 300,000 years after the Big Bang. We were limited to that horizon. With gravitational waves, we can see much further back in time.
So we're probing closer and closer and closer to the Big Bang.
Yes. Now, gravitational wave technology to detect them is relatively new. I mean, the LIGO observatories have been around a long time, but they only successfully found something, got a detection in 2016. So
2016.
Yes. Yeah. Very recent.
Yeah.
So you can imagine the technology's got a ways to go. Back in 2016, it was detection of 1 or 2 or 3 things. Now they actually got a lot better, and we have hundreds of things that blew up and sent a ripple. In the next couple of years, we'll get thousands. So you can see how things get better. But actually, in order to really see all the types of gravitational waves, in particular the ones we are interested in, the ones that come from very close to the Big Bang, you really need to get this technology shipshape.
Right.
And it's expensive. It takes a long time to figure out exactly how to iron out all the wrinkles.
Wonderful. And I think your research on stellar collisions, now I think we're moving close to your research because those stellar collisions can generate, some of them can generate gravitational waves, can't they? Could you tell me about your research and what links it may have with these issues?
Gladly. So stars collide. Sometimes they literally collide like a bullet will hit a tree or something like that. But more commonly, they're born together in pairs, sometimes in more than pairs, triplets, quadruplets, quintuplets. And they live their life together, mostly not really caring so much about one another. They orbit one another, but not much happens. And their own evolution, expansion, contraction, burning through different stages of nuclear fusion will just happen. But then what happens is when they get old, they get big. And when they get big, they might get into each other's airspace. And then mass or gas goes from one to the other. And when that happens, all hell breaks loose. And so you could have all manners of interaction, depending on whether the star's like the sun, for example, or could be 100 times the mass of the sun. It could be a very early star, as in very old star, born a bit near the beginning of the universe. It could be a star that's much more recent. Stars have a lot of characteristics. Depending on those characteristics, these collisions or merging events are different. The interesting ones that generate detectable gravitational waves, the gravitational waves we can see today, are things like neutron stars or black holes. But these stars are actually dead stars. So a neutron star is a tiny little nugget the size of a large island. When I used to live in New York, we used to say the size of Manhattan. So they're 10 kilometers across, really small for a star, but they have the mass of the sun in a tiny little volume. These are basically byproduct of large, massive stars' lives. They are left behind after a big supernova explosion event. And sometimes they are in pairs. So there's 2 neutron stars together, and they go round and round in orbit around one another, losing a little bit of energy every time they go round. And when eventually they lose enough energy, they basically merge. They come close, 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 and eventually become one. That event emits detectable gravitational waves. And we've seen them. They actually are amazing because not only they emit gravitational waves, they also emit light. They're called kilonovae. They emit incredible bursts of radiation, very beamed, like jets coming out of them. And if you're in the path of the jet, you see it, and it is incredibly powerful. They make all kinds of particles, extremely high energy radiation. And I like to study the radiation, and using the characteristics of what we see, we can try and infer the type of physics that went on. Now, neutron stars are so dense that a spoonful will weigh hundreds and thousands of kilograms.
Sorry, could you say that again?
It's a tiny little bit, like a cube of ice of neutron star, will be extremely heavy.
Oh my God.
And so high density. We know already if we take a cube of lead and a cube of wood, the cube of wood doesn't weigh a lot and the lead does. So we understand density. So the lead is denser than the wood. But neutron star material is beyond. Now, when you put that material and compress it in this violent explosions, you can imagine the type of things that happen are really quite beyond what we can test on Earth. So they're actually amazing laboratories of extreme physics. And that is why we are interested. Because
the physics of the Big Bang is seriously extreme physics.
Yes, it is.
Fantastic.
So we basically we have lots of theories, including theories of the Big Bang, but we want to test the theories, right? Theories alone are not very interesting. They need to make predictions, and those predictions need to be coming to pass. So, for example, I say, if you could measure that, you would find these numbers. And the problem is many people will say, well, but I can't measure it if I can't make the experiment. So the universe, the cosmos, gives us the experimental laboratory to make experiments we can definitely not carry out on Earth.
Ursula, I believe that neutron stars play another crucial role in our modern origin story, which is that there are elements that can be created in neutron stars or when neutron stars collide that may not be created in other processes. Is that correct?
That is correct. And in fact, stars of different types in different moments of their life create different elements. So even before we talk about the one element everybody wants to ask about in neutron stars, carbon, which is boring and coaly, actually comes from boring stars like the sun. Loma stars, they get old and they make most of the carbon in the universe. Why is carbon important? Because we are a carbon-based life form. It's relatively abundant. It makes lots of nice bonds, so lots of rich chemistry, hence us. Neutron stars make gold and other things, but gold is the one thing we can all relate to, but that is where it comes from. And for the longest time, there was a theory that neutron stars were the site, the place, so merging neutron stars, were a site or a place where gold is manufactured. But there wasn't very good evidence. And it wasn't until LIGO, the gravitational wave detector, found a gravitational wave source. Telescopes quickly observed the very same spot, found the luminous counterpart of the gravitational waves. It was the neutron star mergers, and they did observe gold lines in the spectrum of the light. The spectrum is a way to analyze the light and tease out all the information. And so we had very good corroboration of that theory.
I didn't know that. Ursula, thank you very much. You've really given me a sense of the mysteries embedded in the idea of the Big Bang. I mean, the mystery of what was there before. There's the mystery of how we can get a better grip on what was happening. And the other mystery that you touched on was this wonderful mystery of whether our brains are so constructed that we will never be able to fully understand the Big Bang.
That is an excellent question. Can we understand the Big Bang? Instead of will we? Can we? Is it even possible? When we think, we often think of mental models. If I tell you, think of a ball on a table, most people will be able to answer questions like, what color is the ball? Oh, it's red. What's the table? Oh, the table's a round table, a square table. Most people really think in those terms. When you do, thinking in n dimensions or 8 dimensions or thinking of string theories probably is not very easy because these mental models are not natural to these theories. So the question I've had for a very long time is, how are you creative? How do you come up with theories when you don't have a way to think of it, a 3-dimensional red ball way to think of it? And I have had this question for a long time. And one day I met a woman who told me that she doesn't have mental models. When you tell her, think of a ball, she has a concept of ballness, but it's not a specific ball. And if you ask her what color is it, she'll say, why is that relevant? You didn't ask me, think of a red ball. You just think of a ball. The ball doesn't have a color in its being a ball. And it turns out there are some people, and I would say neurodiverse people are definitely a good group for that can think more abstractly than that. Now, we all know maths. We all know the rules of maths. The simple ones are 1 + 1 is 2 and 3 + 3 is 6. There are, of course, many more rules than that, and some are really complicated and advanced maths. But they're rules. The rules are laid out in equations, and one equation can be transformed into another equation following the rules. Some people are able to follow these rules in abstract ways without mental models and carry this equation and transform them over and over and over until the equation tells you something extraordinary about the beginning of time, about the nth dimension. And you'll say, but why do you believe it? Well, we believe it because absolutely every time we follow maths and follow the rules, it has predicted things that have come to pass, things that we can measure. So maths has never failed us. There are theories in maths like Australian category theory, and I should boast here, also designed and devised at Macquarie University by Ross Street, also emeritus at this time. I remember asking Ross, what does your theory of mathematics apply to? And he said, it thought for a long time. It couldn't come up with anything. And then he said, it might give a way to describe some flavors of string theory. So the point is, you follow the maths, follow the path, and good things come up that are so abstract that we may not make a nice 3D picture of it, but it will lead the path to understanding the origin of everything.
And you're also saying that people's minds work in different ways, and some people may have minds that can follow the maths. Mine certainly can't, but that some people may have minds that can follow the maths far enough to get a better grip on all of this.
Absolutely. And there are physical theories like quantum physics that are extremely mathematical, and they are very hard to rationalize in a 3D model. And again, quantum physicists, and several exist in my department, and I always ask them, how do you even think? And that's because they lean on the math. And they lean on the maths when there's nothing else. And then they hope that these manipulations lead to something that is interpretable again in answering questions.
Ursula, how can this topic we've been discussing help us understand the past, present and future, which is the very ambitious goal of Big History, of course?
I like to rephrase the question. So understand the past, definitely. The present, it's tricky. The future is about how do we make a better future? How do we forecast the future? How do we improve the future for humanity by having understood the past? I am a big fan of history in general because there's a million lessons there, right? And so, of course, we tend to think of history as human history, but you rightly have shown us that big history is really starting from the beginning. When we understand, we apply the methodology of science, we understand things, we really can carve a future. And I do believe that there are many lessons in astronomy for the future. But one of them is that there are technologies that we develop for astronomy because we want to understand our past that are incredibly useful to generate a better future for everybody. Yes, I think there's a lot of lessons when you dig deep, and the way you're doing Big History is exactly trying to make people do that. Dig deep, think hard, go down to the origin, understand how complexity arises. The first lesson, I think, is that the moment we stop asking these questions this way, we stop being human. And we would often be told by our politicians that this deep research, this fundamental science is not important because there's no immediate application. But the moment we stop doing that, we go back to the cave. Now, we also can tell our politicians that are interested in short-term returns, and we understand why. We can say that there are immediate returns of fundamental science, as fundamental and seemingly useless as astrophysics. And that is that the technologies that we develop to detect the faintest signal, to detect gravitational waves, which are so difficult to do, to hear the faintest radio signal. These technologies have many applications in lots of other fields. Remote sensing, astronomers like to boast that Wi-Fi came from a technology designed by astronomers, by radio astronomers. So there is lots of tangible, immediate applications. It is actually up to the astronomers to really explain this technology so that people who are not astronomers, they're engineers, there are many other types of jobs, can make the most out of it. But then we go back and say, yes, but remember that we also do it because we need to have a sense of belonging, a sense of origin. And that is really the true value, I think, of these sciences.
So asking these big questions, these mysterious questions about the universe, how it came about, how we ended up in the universe, is one of the most profound projects we can engage in as human beings.
It is. And also it's a training ground for asking questions in general. And our society could definitely use a few more people who pause, shut up, and think, does this make sense? Why is that person saying that? Is it even true? idea of fact-checking, understanding information from misinformation. So it is all the same technique. It is about asking questions to make logical sense of things.
Does your head hurt from trying to imagine multiple universes with 8 or 10 dimensions? Because mine sure does. But what a fascinating episode. Our next episode on the origins of life on Earth is equally thrilling. Check out the other episodes of Unknowns, where we explore mysteries and questions about our origins and our future. Interested in learning more about Big History? Check out the Big History Project, a free online course for middle school and junior high students.